Hello class, this is CSE 5250, Section 1, Week 14, Spring 2023, video number 10. Now, for this video, I would like to get to talking about NVIDIA CUDA, but for the interest of time, what I'll do is have this video be a compilation of basically past videos from when I taught this class in earlier semesters. So, what me from the past will be talking about is basically what it looks like to program an NVIDIA CUDA sieve, and what it looks like more in general. If me from the past talks about any assignments later on, those do not apply for this course. So, with that in mind, I'll hopefully by week 15. Well, what I would like to have for week 15 is all of us come back in person for the last week of class and just talk about, well, debugging and basically closing notes for the class itself. So, with that in mind, I'll basically have me from the past talk about NVIDIA CUDA, and we'll basically meet once more, and maybe for the final video for the course, we'll talk about those closing notes. For those of you who aren't able to come in to class in person, at least. Alright, with that in mind, I'll end the video here, and I'll have me from the past take over. Alright, thank you. With that out of the way, I like to start looking at NVIDIA CUDA. Not that you'll be programming anything with NVIDIA CUDA, on account of I can't guarantee that you have access to the necessary hardware, and the installation process does take a bit of time, even if you did have the hardware. But if you're able to follow along, then what you'll find is NVIDIA CUDA is one of the more powerful parallel processing options that we have available to us. So with that, I'm going to start looking at what the sieve of Eratosthenes would look like if we were to use NVIDIA CUDA. So, there are a few minor changes to this sieve compared to the ones we've programmed throughout the class. For one, this one only has one array instead of two arrays. We programmed our sieves to have two arrays. One was an array of numbers, and that was just to keep reference. That was just to keep track of the numbers that we had to go through. Technically, it wasn't necessary because this one only has one array. It is an array that has every integer from 1 to the maximum number we're searching for, and if we encounter a non-prime number in that array, we replace it with 0. Compared that to our sieves that we were using previously, we used that reference array of numbers, and then we had a separate array of bools that we would set to false for every corresponding number that was non-prime. So yeah, this one has a few more optimizations than what I had described throughout the course. And I guess that leads into one thing. If you're going to optimize a program, try optimizing it as much as you can before you consider parallel programming. Because at worst, parallel programming might make the execution time of a function even worse. But I guess but if you've tried benchmarking the sieve already, you may find that it may depend on the workload itself. Also, don't worry if you didn't get any speed up at all. It's more important that you at least tried. Anyway, let's look at this thing. First, let's look at this thing here, which is the function that's to be run on the GPU itself. This is known as a kernel in CUDA. not like the kernel in an operating system. You have to add this global tag right before it. But after that, we write it as we normally would any other function. So this is the if. We are taking in a list of numbers. It's actually an array. We have to also give it the search max, and for our purposes, I'm feeding it the square root of the search max. Now, there are 4 things in here, but we only need to worry about 2 of them for now. The first one is the thread number, and the second one is the thread count. So, that's thread idx.x and blockdim.x. This is basically equivalent to com size and rank. No, rank and com size. Back when we were using MPI. So each thread has its own ID, and each thread knows how many other threads there are. There's also a block count and a block number. This is if you're to use multiple blocks, because threads can come in blocks, and each block can have its own ID. So this becomes important if you're using multiple blocks. But if you're only using one block, you only really have to worry about the thread count and thread number. Alright, so we enter the for loop here. This is the outermost for loop, and typically with the sieve of Eratosthenes, we don't have to go all the way to the search max. We can just stop at the square root of the search max. So that's the outer for loop. We iterate from 0 to the square root of the search max. The num list is an array of numbers, as I said, and it's going to iterate through the array to find a number in that array that was not replaced with a 0. If it was replaced with a 0, that means that number was non-prime. If it's not, we say that is the current prime. At that point, we can enter the inner for loop, but we need to make a few calculations. First, we need to determine the start index for the current thread. Now, in the general case, this code that I'm highlighting, that's all you need. It's going to be, if you have multiple threads and you want to tell each thread a different starting location, as per the case, which is usual for these kinds of things, you want to give it a start index that is based on its thread ID. So for our case, that's basically the thread number. In the case where we want to work with multiple blocks, here's how it works. If you're to use multiple blocks on a NVIDIA CUDA function, if you want to enumerate each thread so that it has a unique ID, you add its thread number to the product of its block number and its thread count. So if you have 4 blocks of 256, you would have thread IDs from 0 to 1023. So if in block 0 you have thread numbers 0 to 255, block 1 would be thread numbers 256 to 511, and so on. Oops. Yeah, in the general case, this is what you really need, but in our case, we're multiplying a few more things to it. Here's how. So we get our starting position by finding this and then multiplying it. No, we add 1 to it and then we multiply it by the current prime. And that's our offset from the starting position, basically. And that's how we got our start index. If you want the stride, that's how much we increment by. It's going to be the number of threads that we have, the thread count, and multiplied by the block count. Now, there is one other optimization here, and it is this. We don't have to increment by 1 for the inner for loop. We can just increment by the current prime. But we can be even more optimized and say, let's increment by the product of the current prime and the stride. That way, the inner for loop only has to work on numbers that are multiples of the current prime number. That isn't the current prime number itself. That's what the +1 means. So basically what this is doing is, suppose we were starting at the number 3. The first thread will start at 6, the second thread will start at 9, the third thread will start at 12, and so on. That way, we'll have a situation where every number encountered by the inner for loop will always be a multiple of the prime number. That isn't already the prime number itself. So, if you're starting at 3, we do not want to eliminate 3 as a non-prime number. We want to eliminate all the multiples of 3 as non-prime. Alright, so that's the sieve itself. We're going to call this in the main function here. And let's walk through that. Okay, so we have our search max. So we're looking for primes up to 10 million. In our case, we're gonna use 64 threads, and for the sake of demonstration, let's use just one block of 64 threads. We have our stopwatch as we did before. Auto start time equals high resolution clock : now. I'm using namespace standard chrono just to keep things short. So normally it would be like standard chrono, standard : chrono, : high resolution clock : now. But if you add using namespace standard chrono, you can shorten it down to just this. Alright, so now what? Well, now we need to allocate memory. So if I hover over this, if you're using Visual Studio and you install the CUDA development thing, IntelliSense will update accordingly so that when you hover over CUDA related functions, you get a description of what it does. So, allocates memory that will be automatically managed by the unified memory system. Basically, we're allocating memory on the GPU. I believe that's what happens. Anyway. Typically a GPU also has its own memory, so you have to tell that thing what you have to tell the GPU what data we're gonna be processing, more or less. Okay, so we allocate memory. We pass it the address of the num list. Technically, this is a pointer to a num list, but we need to pass it. We have to pass in the address anyway, and then we have to pass in how big is this thing in bytes. So we're looking for 10 million. We're looking for numbers up to 10 million. So our search max is going to be that times however big an integer is. So this is basically the size of the array in terms of bytes. Now, excuse me. This array, as I mentioned, is going to be containing all the numbers from 1 to 10 million. So I have to populate it. So for loop numlist I equals I plus 1. So that way it will have all the numbers from 1 to 10 million. The outer for loop only needs to iterate to the square root of the search max, so we have to find the square root of that. So whatever the square root of 10 million is, we store it in here, because we have to pass that later on. Now, numlist 0 is the number 1, and we have to mark that as non-prime. If we forget to do that, it's going to mark every number in the array as non-prime, and we don't want to do that. It nullifies the point of calculating prime numbers because sorry, I'm just thinking. If you had to paint the house and the house is blown up, I guess you could say your work is done because there's no more house to paint. Anyway. Okay, now we get to the fun part. We call the kernel. See this triple chevron here that IntelliSense decided to break? It looks like the chevron and the less than sign, but it's really supposed to look like this. And on the other end, it's supposed to look like this. This is the execution configuration, and it basically tells the kernel how many threads to use. So, I mentioned that we had to set the block count to 1 just to keep things simple. So this is 1, and that says we only need 1 block's worth of threads. So really we need to look at the second number here, and that's the thread count. So, thread count is 64, and we're basically using 64 threads to find prime numbers up to 10 million. So those are the first things you have to pass in. If you can call it passing, if you can think of these as passing these things as parameters, which I guess they're technically not because they're not in the parentheses, they're in these triple chevron things. Anyway. Name of the function, execution configuration, and then the parameters. Those are the num list, the search max, and the square root of the search max. We pass those in, we call the kernel, and then we sync. You have to call the CUDA device synchronize, so wait for compute device to finish blocks until the device has completed all preceding tasks. Oh yeah, these functions here can also return error codes, so in case you have something going wrong and you need to debug, you can store error codes in a variable and you can do debugging that way. In fact, if I'm to make a new project in Visual Studio in 2019 and I said CUDA 11.6 runtime, a project that uses the CUDA 11.6 runtime. Next, let's just name it, let's just leave it as the default name, CUDA runtime, and create. If you decide to follow along with this and try it for yourself, and you installed if you wanted to try this for yourself, the website to download the NVIDIA toolkit is here. developer.nvidia.com/CUDA downloads. You just select what platform you're working on, your operating system version, if it's relevant, your architecture, and then you just download it, and the download is a pretty big file, if you ask me. But once you have that, and you have Visual Studio installed, and you create a Visual Studio project for NVIDIA CUDA, you get this default program. CUDA error_t is the data type for error codes. So, in case you wanted to debug, well, this default program has a lot of, it's got quite a bit of functions related to that, and, hold on, sorry about the interruption. Anyway, this is the default program that is provided to you if you're to use Visual Studio. Anyway, let's get back to the main program that we're looking with. So, okay, so we call the kernel, and then we sync. if we ever have to debug, we can store error codes and debug with that. And once you call device synchronize, that's basically it. And then we can, that's basically it in terms of having the GPU do the work for us. At that point, we can calculate the execution time. Auto stop time equals high resolution clock : now. Then we calculate the execution time, and then we can print that out. And to show that the sieve actually worked, we can print out all the numbers. Just the first prime numbers, just the first set of prime numbers that are less than 1,000. And then after that, we have to call CUDA free, and this is to free memory on the device. Frees the memory space pointed to by dev pointer, which must have been returned by a previous call to CUDA malloc or CUDA malloc pitch. Otherwise, or if CUDA free has already been called before, an error is returned. If dev pointer is 0, no operation is performed. The device version of CUDA free cannot be used, so the dev pointer allocated using the host API and vice versa. So we call CUDA free, and we just free up the memory. We pass in numlist, and that's basically the end of the program. Right, so if you're able to, try this out for yourself, but just in case, I'll just run it for you. And then we can do our own impromptu benchmarks as well. So let's run this and see how long it takes to look for prime numbers up to 10 million. .3 seconds. Let's try it once more just to make sure. 1.2 seconds. Alright, let's do an impromptu benchmark. I'll open up Visual Studio and document recovery. Close that. Let me just zoom in and one, 4, 16, 64, 256, and 1024. For the sake of comparison, let's just looking for primes up to 10 million and looking for primes up to, say, 10,000. Alright, so it took, what, 1.2 seconds on 64 threads, so let's just put in 1.2. Now, let's change this thread count to 256 and try it again. .2, 1.17, 1.18. Now let's call it 1.16. And that was with 256 threads, so let's try 1024 threads. The maximum, by the way, is 1024. I tried this on both my main computer and my laptop, and yeah, it's apparently the maximum number of threads is 1024. So if you tried any greater than that, then the sieve literally won't work. By that I mean, it won't sieve out. By that I mean, the function won't be called, and you'll just get the array that you started with. So nothing will ever. So basically, you'll still get something printed out, but none of the primes were removed. So 1.26 for 1024 threads. So at that point, we're reaching the point of diminishing returns. 1.17. Let's call it 1.17. Now let's go the other way and decrease the number of threads. Let's try 16. And it took 1.67 seconds. Alright, we'll enter that into the spreadsheet. Try it a few times just to make sure. Now, there is a way of automating this entire process by, you need to first build this program, but you can pass in parameters in the main function. So when you call the executable with the command prompt, you can pass in parameters, and that way you can pass in the thread count and the thread count and the search maximum, so you can just, in theory, have a script that would automatically call the function over and over again, and you can even have it so that it writes the execution times to a file. That's just one way to automate this entire benchmarking process. So let's try 4 threads for now. How long does it take? 2.97? 2.966? 2.97? Wait a bit. 2.9? Let's call it 2.9. And if we just wanted to do 1 thread, what happens? Oh boy, it's actually taken a while. 8 seconds, wow. So parallel programming reduced execution time by a factor of 7? Yeah, about a factor of 7. Yeah. Roughly a factor of 7. So that took 8 seconds to execute on just 1 thread. Now, 1E7 is 10 million. If I type in 1E5, that's 10,000. So, let's redo the experiment with only searching for prime numbers up to 10,000. So, all the prime numbers less than 10,000. So, that took 857,000 microseconds, so 0.8 seconds. Run again to make sure. Hello? Not working. Let me try it. There we go. Yeah, 0.8 seconds. So, if I quadruple the thread count again, I get 4. .8 seconds. 0.75. Yeah. Yeah, let's call that 0.75 instead. Increase the number of threads again to 16. Let's see what we get. .83, 0.74, 0.73. Let's call it 0.74. (16 times 4 is 64). So let's try it with 64 threads, as that was the default. 815. This is why it's preferred to do these benchmarks multiple times. So that way you can get an average execution time. So we're getting 0.74 again. So that tells me we're barely getting any sort of speed up at all. Presumably because we're looking for primes within such a short range, or rather, we don't have much parallel work to begin with. So that's why we're not getting much speed up at all. Okay, so one more doubling and that's 256. Are we reaching the points of diminishing returns? Yeah, we've long since reached that point. So what? So 0.72 now? Okay, one more doubling. No, one more quadrupling. I said doubling and I meant quadrupling. Alright, so 1024. .817. Yeah, 0.73. 1 second. So yeah. With a large enough workload, we can use parallel programming to speed up, to reduce the execution time. But if the work was too small to begin with, we don't have to bother with parallel programming at all. So that's one takeaway with parallel programming. When to know when to use it, and if using it has any benefit. I shared a video of using parallel programming to find the seed for a Minecraft world, of all things. And this is a rather interesting project that Minecraft players have taken on, that really tech-savvy Minecraft players have taken on for themselves, and it's basically the essence of the assignment that I had where we brute force the seed for a random number generator, except in the case of Minecraft, you're trying to reverse engineer the world generation for that game to find what seed produced a specific layout of blocks. And people have been successful with these efforts. I've shown the one about finding a tall cactus, but there's also one for finding the seed for a world, but the only image you have is only 128 by 128 pixels. If you're to do this yourself, there's 2 to the 48 power seeds to search for, and that is way too many seeds to look for at any one time. So the efforts of those seed finding attempts involved, among other things, eliminating the possible range of seeds from 2 to the 48th power, which is like 281 trillion, to a more reasonable list, to a more reasonable size of numbers. So instead of just brute forcing your way through 281 trillion seeds, you use, among other things, parallel programs to eliminate seeds that don't fit this requirement, and basically whittle down the list of possible seeds from a really big number to something more manageable that is like a few tens of millions of seeds. Once you get it down to that size, it's easier to brute force because, well, there isn't much. That's way smaller compared to 281 trillion. And at that point, you don't even need parallel programming. You might not even need parallel programming anymore. You only need it for if you have those really big, just really, really big workloads. Speaking of workloads, I'm not sure if I talked about this, but if you're to go into the field of machine learning, or if you're ever going to do anything with a neural network, one thing to keep in mind is that typically neural networks are, under the hood, just a lot of matrix multiplication. And that is one application I want to get into next week, where I tried to make a matrix multiplication program using NVIDIA CUDA. Yeah, I said I would get into that, but I realized it's way more interesting if I try to show it using NVIDIA CUDA. So that's gonna be for next week. If you've ever struggled with matrix multiplication before, I'm gonna illustrate it to the best of my capabilities here. So first I'm gonna draw a pair of matrices. Let's call this matrix A, and it's going to be a 2x2 matrix. So we have a 0, 0, a 0, 1, 1, a 1, 0, and a 1, 1. And then we have another matrix here, and let's make it two rows and 3 columns. So B0, 0, B0, 1, B0, 2, B1, 0, B1, 1, B1, 2. Okay, so matrix A has 2 rows and 2 columns. Matrix B has 2 rows and 3 columns. Now, when we multiply these matrices together, what we end up getting is, well, another 2x3 matrix. That's because matrix A has these row vectors that are of size 2, and matrix B has these column vectors of size 2. So basically the number of rows of matrix A, the number of columns of matrix A has to match the number of rows of matrix B. I hope this is making sense. But basically, this is how you multiply 2 matrices together. So we get this matrix C, that's the product, and it's going to have entries C01, C00, duh. C01, and C02, and then C10, C11, and C12. And since I have these 2 vectors highlighted, how do we calculate C00? Well, it's simple. It's a dot product. When we take a dot product, we do this. Since I have these two highlighted, so let's calculate it. So C00 equals A00 times B00 plus A01 times B10. So basically, for each row vector of matrix A, we're going to multiply it with each column vector of matrix B. Let me just write this down in words. So for each row of matrix A, we multiply it with each column of matrix B. These are the values for... These will become the values of each row of matrix C. So if we rewrite this in code, we would have something like... We would basically have a nested for loop. So it would look something like this. Okay, so we have our doubly nested for loop, but it's actually a triply nested for loop because to go through the two vectors requires a third for loop, so we have to iterate through each pair of values, so like that, and that. So really, and typically how this is taught is we have a triply nested for loop, so and then the third for loop is basically iterating for each entry in row and column. So really what we need is a for loop that does this. K is less than the number of columns of A. So let's just call it A COL. So yeah, the innermost for loop is going to do a dot product calculation, and the other two outer for loops are going to iterate through every row vector of A and then every column vector of B. So let's look at this in code. Okay, so I have a matrix here, and this first function is actually going to print out the matrix, so this is just to make sure the entire thing is working. What we really want to look at is this function here. This is a matrix multiplication function, and it's going to take in two matrices. It's going to find the size of the two matrices. It's going to find the sizes of the two matrices, and it's only going to work if the number of columns of A is the same as the number of rows in B. If that's not the case, in this example, I'm just going to return an empty matrix. The next step is to create an empty matrix that's going to be the size that's going to have as many rows as A, but as many columns as B. So the product matrix is going to be of that size that I mentioned. Then we enter that triply nested for loop. We're going to iterate through the rows of matrix A, then the columns of matrix B, and for each combination of row and column, we're going to find that dot product and then store that somewhere in matrix C. So we have I and J for our iterators for the rows and columns, and then we have K to iterate through the vectors themselves. So Cij is going to start at 0 because I populated the C matrix to be full of zeros. So we're going to increment it by Aik times Bkj. And that's going to be the entire calculation right there. If we go into the main function, I already had a few examples where I tried it out with a few pre-made matrices. Here is just a for loop. Here's just a pair of for loops where I populate the matrices with different values, but I specify the size. So yeah. And then we have a third matrix that's going to be the product of the two matrices. Product matrix is 2 rows by 4 columns. That's actually from these ones. So really it's going to be X columns by Y columns. For one matrix is going to be X. No. Really it's going to be 2 rows. Yeah. These two matrices that I commented out, they would produce a product that's 2 rows, 4 columns. Here I have matrix A, B, X columns, no, X rows, Z columns. Matrix B is Z rows, 4 columns. If I multiply those two matrices together, I get a matrix that's X columns, no, X rows, Z columns. And if I just run it, I have to enlarge it because there's so much to show. I have our two matrices here, and then I have the product matrix here. So, how do we make this parallel? One way to do this is to use OpenMP. We looked at OpenMP when we were writing the sieve of Eratosthenes in a few different ways. And of course the first one was to use OpenMP. You may have found that to use OpenMP may be the easiest way of making something parallel, because it's just as simple as looking at the code, recognizing where code can be made parallel, and then just adding a few directives, and that's it. So one way to do it is to add the pragma OMP parallel for on the third for loop. And to make sure that this thing will work properly, not options, I'm going to go to project properties and go to configuration properties C/C++ language, and then I can turn on OpenMP support. And that's it, right? Well, let's take a close look. We have 65, 72.8, and 80.6. And if I run it again, actually what I'm going to do is I'm going to modify the code so that it's going to produce two matrices, but every entry in each matrix is going to be the same value. So let's just push back a 1 in the first matrix, and then a 3 in the second matrix. So what do we get? Now, because all the row make, because all the because all the row and column vectors are going to be the same, we should get the same value, but we're not. And that's because we've accidentally introduced a race condition, and that's because we have multiple threads trying to access the same thing by incrementing it, and we get a synchronization issue that we can resolve by adding pragma OMP critical. And now we get the correct answer. The product matrix is just a matrix full of 36s. That is one way to do it. Another way to do this is to recognize that the dot product calculation is its own for loop, and we just have to iterate through the. We can just iterate. When we iterate through the rows of matrix A, we're gonna iterate through the rows of. We iterate through the rows of matrix B, and then we iterate through the columns of matrix B. What could also work is if we just add the compiler directive on the second for loop. It's going to parallelize the work of this for loop, but not this one. Or rather, it's gonna be done in such a way so that every loop iteration is going to have its own dot product calculation. So to make sure this works, it works. 1s, 3s, and 36s. Alright, so what I can have you do is play around with this program and have you see for yourself how this works. I have the code available on Canvas after all. But what I also have available on Canvas is a CUDA implementation of the sieve of error. No, not the sieve of Eratosthenes. Well, I actually do have a sieve. I actually do have a CUDA sieve. But what I also have is a matrix multiplication program that's programmed using CUDA. So I'm gonna pause the video real quick and I'll continue right from there. Right, so I'm back. So if you were to download the NVIDIA CUDA toolkit that I may have shown a few times already, if you're to start up Visual Studio, you're going to have an option to make an NVIDIA CUDA project. And it's going to populate the entire kernel.cu file with a default program. I've already erased most of that, but really what we need at the least is this include CUDA runtime.h and include device launch properties.h. If you look here, we have the kernel here that's going to run on the GPU, and I've already coded it so basically what's going to happen is this. Sorry, excuse me. So what's going to happen is this. You know how we had that triply nested for loop where we had to iterate through the rows of one matrix and then the columns of another matrix? Well, we're going to attempt to do every dot product calculation all at once. And here's how. Basically, we're going to divide the work in such a way so that we're going to have the work on this grid of threads. So we have thread idx.x and thread idx.y here. Those are going to correspond to our rows and columns because each thread is going to have a row and column identifier, you could say. Each thread is effectively going to calculate every across all the threads, it's going to calculate every dot product. But it's going to have to do it one step at a time because it still has to iterate through the pairs of vectors individually. So there are a few catches to this particular example. Mainly, it's going to only work on square matrices. So I guess that's fine for this example. But anyway, yeah, we're gonna have a whole bunch of threads on this grid. And this if statement here is just here to make sure if we have any rows and columns outside the bounds of the matrix, whatever thread is going to try to do that work, it's just not going to. So it's basically only gonna calculate if that thread is somehow within the bounds of the product matrix, if that makes sense. I also have a print matrix function here, similar to the one we had before. Now there is another catch. I had to write the matrices as a one-dimensional array instead of a two-dimensional thing. If you look at the previous example, I coded the matrices so that it's a vector of doubles. That's what this type def means. It's basically a shorthand for me to say, hey, when I say matrix, I really mean a vector of doubles. Instead, I have to have my matrices be a 1D array that's supposed to represent a square matrix of n by n. So it's going to have n squared entries. But that's okay. Sometimes we have to represent matrices that way anyway. Okay, so since these are being declared on the they're being declared on the computer, but then we have to allocate memory on the GPU so that the GPU knows what these things are. So we call CUDA malloc managed. We pass in the address for the three matrices. Matrix A and matrix B are going to be the two matrices we're multiplying together. Oh yeah, as a reminder, matrix multiplication is not commutative. So if you multiply two square matrices A and B in that order, if you swap them so it's B times A, you'll not get the same matrix. You get non-commutative examples like that all the time, such as, hold on. Right, so you get non-commutative operations a lot of the time where the order of operations matter and you can't mix them up. So, for example, if I twist this side into the top, it's going to be different if I did it top and then the side. I mean, look, I don't know if you can see this, but the outcomes are different. Here we have a on one cube I have 3 blue tiles in a row, on the other one it's 3 white tiles in a row. See, non-commutative. Anyway, so we allocate memory on the GPU, and then I'm gonna populate these matrices with values so the kernel has something to work with. Of course, you can just do something else, such as read from a file or do some other way of populating a matrix. But whatever it is, we're gonna have to populate matrix A and B with some values, and then we're gonna populate matrix C with zeros. And then I'm gonna declare these dim trees. It's going to set a specific number of threads for us to work with. The easiest way to do this is if we have this threads per block value be set to n and n. So it's going to work with n by n threads. This blocks per grid, we can just set it to 1 and 1. because we only need to work with one block's worth of threads. And then we can just pass it into the angle brackets here. We call the kernel, we tell it how many blocks per grid, and then we tell it how many threads per blocks. We pass in matrix A, B, and C, and we also have to pass in N, which is, well, the size of the matrix. We call CUDA device synchronize. We print the matrices to see what it's done. We deallocate memory when we're done, and that's basically the end of the program. So let's try to run that. Right. 0.1, 0.2, 0.3, yada yada yada, 0.25, 0.5, 0.751, and so on. Maybe it would help if we just tried a much simpler example. So I'm just gonna set these two matrices to have just one value. One is gonna be full of ones, the other one's gonna be full of threes. So when we do our multiplication operation, it's literally gonna be the same calculation for every entry in the product matrix. So, oops. 1, 1, 1, 1, 1, 1, 1, 3, 3, 3, 3, 3, 3, 3. Multiply 1 and 3 together, and we get a bunch of trees, but then we have to add all the trees, and we get 48. And there we go. Now, I am referencing a tutorial on this. It's linked in the comments, but I also have it linked on Canvas. So basically, let me just get the article. Hold on. Alright, I got the link. It is quantstart.com, and it's an article on how to do matrix multiplication. Now, with this threads per block and blocks per grid thing here, there is a maximum size that we have to keep in mind, and it's 512. So whatever size n is, n squared cannot exceed 512. So there's a max size to this. Yeah. My example here is programmed a little bit differently, but it tries to capture the gist of what's going on. But as a curiosity, 512. The square root of 512 is something like 22.6. So it means there is a maximum size on these matrices. To multiply matrices bigger than that will require a bit more coding, but this is for, I guess we can say this is for matrices smaller than, say, 22 by 22. So I think we're, so I guess I can say we're good on matrix multiplication. If you want to try multiplying even larger matrices, we're gonna have to do some level of rewriting to make this work. But for now, I'm gonna stop talking about matrix multiplication, and then I'm gonna go back to a program that I shared that we can also try to make parallel. So